Okay, class, what we're going to be talking about today is 6.5, definition and property of trapezoids and isosceles trapezoids. Um, if you can flip over to the objectives page, please, and we'll look at the focus. So as we look at the three objectives, the first objective, we're just recalling the umbrella of the quadrilateral family. And then second, we're going to take a look at recalling the definition of parallelogram, rhombus, rectangle, and square. We are actually not going to cover the properties again. We're just going to focus on the definitions for parallelogram, rhombus, rectangle, and square. And then third, which is the main focus of today, the new objective, which you should know and use the definition and properties of trapezoids and isosceles trapezoids. So let's quickly review the relationships among the different types of quadrilaterals. Um, so if we take a look here, at the very top, the most general name in this chapter, we're going to use the word polygon. And as we go down this flow chart, we're going to get more specific. So a little bit more specific than polygon is quadrilateral. Okay, and again, a quadrilateral is a four-sided polygon. And then as we veer off to one side now and get a little bit more specific, off to this side we have the parallelograms. And we're going to get into the definition again of parallelogram here in a second, I believe on the next page. Now there's three special kinds of parallelograms. And as we go down for the three special kinds of parallelograms, we get the most specific one at the very bottom, or the coolest friend of the whole group. So as we work down, we got rhombus. A rhombus is definitely a parallelogram. And then we have a rectangle. And then the coolest of the three special kinds of parallelograms is a square. And why is a square the coolest parallelogram? Because a square has all of the properties of a rectangle and all of the properties of a rhombus. Therefore, it's the coolest of the three special kinds of parallelograms. And again, we'll talk about the definition of a parallelogram in a minute and why a rhombus, rectangle, square qualify as being a parallelogram. Off the other direction, we have some four-sided polygons that are not parallelograms, and we'll get into that. And those will be trapezoid. And again, as we go down the flow chart, get a little bit more specific, then we have a real cool kind of trapezoid, and that would be known as an isosceles trapezoid. So this is what the flow chart looks for this chapter. Okay, again, today we're going to focus on definition and properties of trapezoid and isosceles trapezoid. You can flip over to the very next page. What we're looking at here is recalling the properties, the definition of parallelogram, rectangle, rhombus, and square. We're not going to focus on the properties again. So if we're looking here, objective 2 is recognizing we're just focused on the definition of parallelogram, rectangle, rhombus, and square. Okay, so for parallelogram, the definition, as you might recall, is a parallelogram, and I won't write it there, but you can. A parallelogram, by definition, is a quadrilateral in which both pairs of opposite sides are parallel. So again, the definition of parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. And this is what it would look like in terms of markings, based upon the definition that I just gave. AB and DC being parallel would be one pair of opposite sides parallel. And then we actually have segment AD parallel to segment BC, which would be the second pair of opposite sides parallel. Hence the definition of parallelogram. Everything else off of a parallelogram are known as the properties of a parallelogram, which we won't get into again. I just wanted to recollect the definition of parallelogram. Quadrilateral on which both pairs of opposite sides are parallel. Moving on to rhombus. The definition of a rhombus is a parallelogram in which two consecutive sides are congruent. So by definition, a rhombus is a parallelogram, which means it has both pairs of opposite sides parallel, in which at least two consecutive sides are congruent. Okay, so again, it's a parallelogram, which means both pairs of opposite sides are parallel, in which at least two consecutive sides are congruent. And I just marked that there for you. So there's two consecutive sides. The word consecutive means in a row. So the definition of a rhombus is a parallelogram in which at least two consecutive sides are congruent. Everything else flows as a property of a rhombus, in which we've already covered. Moving on to rectangle. The definition of a rectangle is a parallelogram that has at least one right angle. So the definition of a rectangle is a parallelogram that has at least one right angle. A parallelogram that has at least one right angle. So you notice, because a rectangle is also a parallelogram, it has both pairs of opposite sides parallel, that it has at least one right angle. Okay? Everything else that stems from a rectangle are known as the properties of a rectangle, but the definition of a rectangle is a parallelogram that has at least one right angle. By definition, everything else flows as a property. Moving on, last but not least, of reviewing the definitions of the three special kinds of parallelograms is a square. By definition, well, let me just say this. If we went back to that flow chart and we looked at the three special kinds of parallelograms, you would notice that the square was way at the bottom, below the rhombus and the rectangle of the three special kinds of parallelograms, which indicates to us that the square is the coolest friend of the three. The square is pretty hip, okay? Why? Because a square is a parallelogram that is both a rectangle and a rhombus. Let's do that again. A square is a parallelogram that is both a rectangle and a rhombus. A square is a parallelogram that is both a rectangle and a rhombus. In other words, what we're saying is, because the square is the coolest friend of the three, the square has all of the attributes of the rectangle and all of the attributes of the rhombus. That's why it makes it the coolest. It has the most stuff. All right, if we flip over to the next slide, the focus of today in the new lesson is objective 3. No one used the definition of properties, no one used the definition and properties of trapezoids and isosceles trapezoid. Well, a trapezoid is definitely a quadrilateral, just like all of the three special kinds of parallelograms and a parallelogram. It's a quadrilateral like those, except the trapezoid is not a parallelogram because it doesn't have both pairs of opposite sides parallel. That's why on the flow chart, trapezoid and isosceles trapezoid veer off to the right, not the left. Okay, a trapezoid by definition, if you want to write that in that blank, a trapezoid by definition is a quadrilateral in which one pair of opposite sides are parallel. A quadrilateral in which one pair of opposite sides are parallel. In this case, I denoted segment AB and segment DC being the one pair of opposite sides parallel. Okay, that is the definition for trapezoid. Some other things we want to note, okay, that still holds true. That definitely, if these two lines are parallel, that I'm now highlighting, and we utilize segment AD as the transversal, we still need to recall, and it does hold true, just like it does for all of the parallelograms, that same side interior angles are supplementary, where I put the two dots. So we're saying that because those are two parallel lines cut by that green transversal, that angle A, that the measure of angle A plus the measure of angle D has to equal 180 degrees. Those angles are supplementary. If we apply the parallel lines again and now use segment BC as the transversal in blue, now we have same side interior angles over there. So again, we need to understand that if two parallel lines are cut by a transversal, then same side interior angles are supplementary. So in this case, the measure of angle B plus the measure of angle C equals 180 degrees. Okay? Again, the definition of a trapezoid is a quadrilateral that has one pair of opposite sides parallel, but then we still need to remember that if those lines are parallel and using the transversal as I just showed 2 different times, we have 2 pairs of supplementary angles. Okay, let's put this into play. Example 1 says show that ORST is a trapezoid. Well, the only way to show that ORST is a trapezoid is to show that one pair of opposite sides are parallel. Okay, so given this quadrilateral in a 2-dimensional coordinate plane, we must try and show, in this case, somehow that segment RS is parallel to segment OT. Well, what we recall, or I'm going to help you recall from algebra, that is if 2 lines are parallel, their slopes are the same. So if 2 lines are parallel, their slopes would have to be the same. So if we can show that those 2 blue segments have the same slope, then those 2 segments are definitely parallel, now making that quadrilateral a parallelogram. So what we want to do is find the slope, of segment RS. And the slope of segment RS is going to be found by taking y sub 2 minus y sub 1 and dividing it by x sub 2 minus x sub 1. So if we take point R, which is 0, 3, and take point S, which is 2, 4, now let's label point R as first x, first y, and point S as second x, second y. Substitute those values in the slope equation to find the slope of segment RS. So the slope of segment RS is going to be 4 minus 3 divided by 2 minus 0. When we simplify this ratio, we get 1/2. So 1/2 is the slope of segment RS. So now we need to find the slope of segment OT and then see if it is the same as the slope of segment RS. If it is, we're in luck, and these 2 lines are parallel, now making that quadrilateral a parallelogram. Okay, so taking point O, which is 0, 0, the origin, and taking point T, which is at 4, 2, again labeling these points. That's going to be first x, first y, second x, second y. Okay, now substituting those values into the slope equation, we have the slope of segment OT is going to be 2, y sub 2 is 2, minus y sub 1, 0, divided by x sub 2, which is 4, minus x sub 1, 0. And if we simplify this ratio, we get 2/4. Okay, but then we got to reduce this ratio by dividing this ratio by the greatest common factor, which is 2. So this ratio does indeed, 2 divided by 2 is 1, and 4 divided by 2 is 1/2. So the slope of segment OT is 1/2 as well. So what we notice is that the slope of segment RS is 1/2, and the slope of segment OT is 1/2. And therefore, because the 2 slopes are the same, I now know these 2 lines or segments are parallel because their slopes are the same. Now classifying that not only as a quadrilateral, but now being able to classify it as a trapezoid. If we flip over to the next slide, okay, moving on to isosceles trapezoid. By definition, obviously, an isosceles trapezoid is a special kind of trapezoid. Okay, so if it is a trapezoid, it still holds true that you have one pair of opposite sides parallel. But what's new is, now that it's an isosceles trapezoid, we have one pair of opposite sides parallel and the other pair of opposite sides congruent to one another. So by definition, isosceles trapezoid is a trapezoid that has one pair of opposite sides parallel, that'd be segment AB and DC, and the other pair of opposite sides being congruent, segment AD and BC. Everything else will follow as a property. So let's go through the properties if you want to fill them in the blanks. One of the properties of an isosceles trapezoid is that the diagonals are congruent to each other. So highlighting those diagonals now, segment AC is congruent to segment DB. So in an isosceles trapezoid, we know that the diagonals are congruent to each other. If you want to fill in number 3, which is another property of an isosceles trapezoid. In an isosceles trapezoid, the lower base angles are congruent and the upper base angles are congruent to each other. So in that blank 3, if you want to write, another property of an isosceles trapezoid is that the two lower base angles are congruent and the two upper base angles are congruent. That'd be in blank 3. Okay. In blank 4, which would be another property of an isosceles trapezoid, is that one upper base angle and one lower base angle will be supplementary. One lower base angle and one upper base angle will be supplementary. And I'll write that out for you. So the measure of angle DAB plus the measure of angle ADC equals 180 degrees. So one upper and one lower base angle is supplementary. That's one pair, but there's another pair. Also, the measure of angle ABC plus the measure of angle DCB equals 180 degrees. Okay. I think I have too many blanks here. I'm going to double check now. Let's review to see what we got and how many blanks we have filled in. So by definition, the first blank, number 1, a trapezoid, an isosceles trapezoid is a trapezoid that has one pair of opposite sides parallel and one pair of opposite sides congruent. That's the definition. And blank number 2, one of the properties should be that the diagonals are congruent. And then this may not be in the same order that we stated them the first time, so just check to make sure that you have these properties. I don't remember what we said. In another property blank, we should have that the lower base angles are congruent and the upper base angles are congruent. So the lower base angles are congruent and the upper base angles are congruent. And then somewhere for one of the properties, you should have written down next that one upper base angle and plus the measure of one lower base angle equals 180 degrees. So one upper base angle and one lower base angle are supplementary. So we have 2 pairs of those. I apologize, there might be extra blanks here. I just noticed that. If we flip over, let's put this into play. In example 1, it says PQRS is an isosceles trapezoid. Find the measure of angle P, the measure of angle Q, and the measure of angle R. Also find QR's length. Okay, let's start by finding the measure of angle R, or using 3 letters, as R is a vertex, let's find the measure of angle SRQ. Well, the measure of angle SQRU, SRQ, I wrote that wrong, my apologies, SRQ, okay, middle letter R, so R is the vertex, has to equal 50 degrees if this is an isosceles trapezoid. Why? Because in an isosceles trapezoid, the 2 lower base angles are definitely congruent. So the measure of angle R definitely has to be 50 degrees. So that takes care of the measure of angle R. Now, if we look at how to find the measure of angle P, or using 3 letters, the measure of angle SPQ. Okay. Again, if these 2 lines are parallel, cut by this transversal, then these two same side interior angles are definitely supplementary. So when 2 parallel lines are cut by a transversal, same side interior angles are supplementary. So let's write that out to find the measure of angle P. So we got the measure of angle RSP, which is 50 degrees, plus the measure of angle SPQ have to equal 180 degrees. Okay, that'd be this angle plus this angle, or the 2 we just named, have to be supplementary. So substituting in what we know about the measure of angle RSP, 50 degrees, plus the measure of angle SPQ have to equal 180 degrees. Then solving this equation by subtracting 50 from both sides, we get that the measure of angle SPQ equals 130 degrees. Middle letter point P, so P is the vertex. So angle P is 130 degrees. So if we erase that dot I just put there, we now know this angle is 130 degrees. We also found the measure of angle R already. Now all we need to do is find the measure of angle Q next. And angle Q and angle P are the upper base angles. And the upper base angles are definitely congruent to each other. So if the measure of angle SPQ is 130 degrees, then definitely the measure of angle PQR is also 130 degrees. Now you may be inclined to call angle P and angle Q the lower base angles and call angle S and angle R the upper base angles. And I could see why you would do that, and I would be fine with that. I was looking at it as the isosceles trapezoid was flipped upside down. So we found the measure of angle Q. And now we just need to find the length of segment QR. Well, if this indeed is an isosceles trapezoid, then we have one pair of opposite sides that are congruent. So if segment SP is 7 units, then 7 inches, excuse me, then definitely segment QR is also 7 inches. So the length here is 7 inches. If we move on down to the next example, it'd just be another example exactly of the one we just did above. So if you want to go ahead and take a few minutes to try this example, it's just exactly the same as the one we just did with different values in there. Last but not least, talking about the trapezoid mid-segment theorem. The mid-segment of a trapezoid is parallel to both bases and is 1/2 the sum of both of the bases. And there you see the mid-segment equation. Okay. Bottom line is this: in a trapezoid, if point M is a midpoint over here, which it is, and how do I know that? Because this segment is congruent to this segment by the tick marks. And if point N is the midpoint over here, and of course it is because segment QN is congruent to segment NR, then segment MN is known as a mid segment in that trapezoid. And to find the length of the mid segment in a trapezoid, you take the length of the 2 bases, which I just highlighted in blue and green, and you add them and take half of that. So the mid segment, which is in red, that segment MN, is equal to 1/2 the sum of the length of the 2 bases. Well, what are the base lengths? The blue segment is one of the bases, which is 12, and the length of the other base length is 28 inches, which is in green. So the length of the mid segment MN is going to be 1/2 the sum of 12 plus 28. So 1/2 of 40 is 20. So the length of the mid segment NN is going to be 20 inches. Okay. Looking at this from a different perspective, using the same equation, Okay, in example 2, it says segment EA is the midsegment of the trapezoid, which now means point E is a midpoint, and now means point A is also a midpoint. We're not looking for the midsegment length in this case. We actually know what the midsegment length is, and we're actually trying to find the length of one of the bases. But we're still applying the same equation. So, the midsegment equation. We know the midsegment length, and we know that it's half of the sum of the two bases. Well, one of the bases is represented as a variable z plus the other length of the other base, which is 24. So now we're just looking for one of the base lengths. So what you want to do here when we know the midsegment and we're looking for one of the base lengths is divide both sides by half first. And when you divide a number, a whole number by a fraction, your answer better be bigger than 18, not smaller. And in fact, in this case, when we're dividing by half, it should be twice as big as 18, so it should be 36. Now deriving that equation, subtracting 24 now from both sides, you get z is equal to 12 inches. So the length of segment FR is 12 inches, utilizing the mid-segment equation from a different perspective. I believe that's all we have for today. I appreciate you tuning in.